Imagine staring at a photograph taken just moments after the universe was born. A snapshot so ancient it captures the first whispers of light flickering into existence. This isn't science fiction, it's real. That faint glow, nearly 14 billion years old, still reaches us today, carrying secrets from the very dawn of time. This is the cosmic microwave background, or CMB, the universe's oldest light. It's like a cosmic baby picture, a frozen moment from when everything we know was just beginning to take shape. And what's even more astonishing, this ancient light isn't just a relic of the past, it's a treasure map, revealing clues about how galaxies formed, how space itself expanded, and even hinting at mysteries we're still trying to unravel. Think about this for a second. Every time you tune an old television to static, a tiny fraction of that snowy interference is actually the CMB echoes of the Big Bang itself. It's everywhere, all around us, a silent whisper from the universe's infancy. Scientists have spent decades decoding this light, peeling back layers of cosmic history like reading the rings of an ancient tree. And what they've discovered is nothing short of mind-blowing. The CMB holds patterns, tiny fluctuations in temperature that tell the story of how matter clumped together to form stars, galaxies, and eventually us. Without this faint glow, we'd be stumbling in the dark, missing the very blueprint of our existence. But here's the thing, the cosmic microwave background is more than just a scientific curiosity. It's a bridge between us and the universe's earliest moments, a connection to something unimaginably vast and ancient. Over the course of this video, we're diving into 30 astonishing facts about this primordial light, each one more fascinating than the last. From how it was accidentally discovered by two radio astronomers to the way it's reshaping our understanding of dark matter and dark energy, these aren't just dry facts, they're pieces of a cosmic puzzle that's still coming together. So if you've ever looked up at the night sky and wondered how it all began, stick around, because by the time we're done, you'll never see the universe or that static on your TV the same way again. To put this into perspective, the cosmic microwave background is like a message in a bottle, drifting across an ocean of time for nearly 13.8 billion years. It was emitted when the universe was just 380,000 years old, a cosmic toddler taking its first steps out of the fiery chaos of the Big Bang. Before that moment, the universe was a seething plasma, so hot and dense that light couldn't travel freely. It was trapped, bouncing endlessly between particles like a pinball. But then, as the universe expanded and cooled, electrons and protons finally combined to form neutral hydrogen atoms. Suddenly, light broke free, streaming outward in all directions. That first burst of light is what we now detect as the CMB, a snapshot of the universe's toddler phase, frozen in time. What makes this light so extraordinary is its sheer endurance. It has traveled for longer than stars have existed, longer than galaxies took shape, longer than Earth itself formed. Every photon we detect from the CMB has been journeying since the dawn of creation, carrying untouched information about the universe's infancy. Think of it as opening a time capsule buried by the cosmos itself, one that hasn't been disturbed or altered for billions of years. But here's where it gets even more fascinating. The CMB isn't perfectly uniform. Tiny variations in its temperature, less than 1/100th of a degree, act like cosmic fingerprints. These fluctuations are the seeds of everything we see today. The blueprint for galaxies, galaxy clusters, and the vast cosmic web stretching across the universe. Without those subtle ripples in the ancient light, matter wouldn't have clumped together, gravity wouldn't have sculpted the structures we know, and we wouldn't be here to study it. So when astronomers map these temperature differences, they're essentially reading the universe's first recipe, written in the faint glow of its oldest light. And yet, despite being so ancient, the CMB isn't static. The expansion of the universe has stretched its wavelengths over time, shifting the light from visible brilliance into the microwave range, hence its name. This is why we can't see it with our eyes but can detect it with specialized instruments like the Planck satellite and the Atacama Cosmology telescope. Each new observation peels back another layer, revealing more about the conditions of the early universe. In a way, studying the CMB is like rewinding a cosmic film reel to the very first frames. It's our most direct link to the Big Bang, a window into a time before planets, before stars, before atoms as we know them. And with every discovery, we're not just learning about the past, we're uncovering clues about the universe's ultimate fate. Will it expand forever? Could there be hidden dimensions or parallel universes imprinting their signatures on this ancient light? The answers might be hiding in those faint microwave whispers, waiting for us to listen just a little closer. Sometimes the biggest discoveries in science happen when you're not even looking for them. That's exactly what happened with Arno Penzias and Robert Wilson, two radio astronomers who accidentally stumbled upon the cosmic microwave background while trying to solve what seemed like an annoying technical glitch. Back in 1964, these two researchers were working with a massive horn-shaped radio antenna in New Jersey, originally designed for satellite communication experiments. But no matter where they pointed it, they kept picking up this strange, persistent noise, a faint hiss that wouldn't go away. At first, they thought it was just interference. Maybe it was static from nearby New York City, or perhaps pigeons had nested in the antenna and left droppings that were causing the signal. They even cleaned out the antenna and shooed away the birds, but the noise remained. What they didn't realize at the time was that this stubborn hiss wasn't a flaw in their equipment, it was the sound of the universe itself. Meanwhile, just 30 miles away, a team of physicists at Princeton University, led by Robert Dick, had been actively searching for this exact signal. They theorized that if the Big Bang had really happened, there should be some remnant heat, a faint afterglow lingering in space. When Penzias and Wilson heard about this theory, the pieces suddenly clicked. That mysterious noise wasn't a mistake. It was the oldest light in the universe, cooled and stretched over billions of years into microwave static. What's incredible about this discovery is how perfectly it aligned theory with observation. Scientists had predicted the existence of this cosmic background radiation, but no one expected it to be found by accident. Penzias and Wilson weren't even looking for it, yet their persistence in chasing down an unexplained signal led them to one of the most important cosmological confirmations of the 20th century. In 1978, their serendipitous discovery earned them the Nobel Prize in Physics, proof that sometimes the universe reveals its secrets in the most unexpected ways. The irony is delicious. Two scientists trying to eliminate background noise ended up detecting the ultimate background noise, a whisper from the birth of everything. Without their curiosity and thoroughness, we might have taken much longer to confirm the Big Bang theory. Their story is a reminder that in science, sometimes the greatest breakthroughs don't come from grand experiments or deliberate searches, but from paying attention to the little things, the unexplained signals, the persistent anomalies. Because buried in those nuances might just be the answers to our biggest questions about the cosmos. The cosmic microwave background isn't just a distant echo. It's everywhere, in every direction, saturating the universe like an invisible ocean of ancient light. No matter where you point a radio telescope, whether toward the brightest galaxy or the emptiest patch of space, you'll detect the same faint glow. This omnipresence is one of the most profound clues we have about the universe's infancy. It tells us that long before galaxies formed, before stars ignited, the cosmos was a remarkably smooth and uniform place. Picture a balloon inflating. As it expands, every point on its surface moves away from every other point. The CMB works the same way. Its near-perfect uniformity, varying by less than 1 part in 100,000, suggests the early universe was incredibly homogeneous, a vast sea of hot plasma with barely any lumps or variations. But here's the catch: if everything was so smooth, how did galaxies and galaxy clusters eventually form? That's where those tiny temperature fluctuations come in. They're the universe's way of breaking its own symmetry, like subtle ripples in a pond that eventually grow into waves. What's truly mind-bending is that this uniformity stretches across distances that shouldn't have been able to communicate with each other in the early universe. Light hadn't had enough time to travel from one side of the cosmos to the other, yet somehow, regions billions of light-years apart share nearly identical temperatures. This cosmic conundrum led scientists to propose the theory of inflation, a brief but unimaginably rapid expansion of space in the first fractions of a second after the Big Bang. Inflation would have stretched quantum fluctuations into the larger-scale variations we see in the CMB, planting the seeds for all structure in the universe. But the CMB's omnipresence does more than just hint at inflation. It also acts as a cosmic anchor, a reference point that helps astronomers map the universe's geometry. Because this light has traveled for so long, slight distortions in its patterns reveal how space itself is curved, whether it's flat like a sheet of paper, positively curved like a sphere, or negatively curved like a saddle. The latest measurements overwhelmingly suggest a flat universe, one that will keep expanding forever. And yet, despite its uniformity, the CMB isn't perfectly smooth. Those minuscule temperature differences, some spots slightly hotter, others cooler, form a cosmic fingerprint, a snapshot of density variations in the infant universe. Hotter spots mark regions where matter was slightly denser, places where gravity would eventually pull material together to form galaxies and clusters. Cooler spots, meanwhile, trace the emptier voids between them. It's a blueprint written in microwaves, a roadmap of how the universe grew from a nearly featureless fog into the intricate cosmic web we see today. So when we say the CMB fills the entire universe, we're not just talking about a faint glow. We're talking about a living relic, a direct line back to the universe's simplest, most primordial state. It's the ultimate background radiation, the afterglow of creation itself, and it's still teaching us fundamental truths about where we came from and where we're headed. The cosmic microwave background isn't just a relic, it's a cosmic ledger keeping meticulous records of the universe's ingredients. By studying the subtle patterns in this ancient light, scientists have pieced together a staggering revelation. Everything we can see, stars, planets, even ourselves, makes up a mere 5% of the universe. The rest, a mysterious cocktail of dark matter and dark energy, invisible forces shaping the cosmos in ways we're still struggling to comprehend. Here's how it works. Those tiny temperature fluctuations in the CMB aren't random. They follow precise mathematical patterns like ripples frozen in time. When researchers analyzed these ripples using satellites like Planck and WMAP, they noticed something extraordinary. The spacing between hot and cold spots didn't match predictions based on visible matter alone. The only explanation: there had to be something else out there, something invisible tugging at the fabric of the universe. Enter dark matter, an enigmatic substance that doesn't emit, absorb, or reflect light, yet outweighs ordinary matter by a factor of 5. But the surprises didn't stop there. The CMB also revealed that the universe isn't just expanding, it's accelerating, as if some unseen force is pushing galaxies apart faster and faster. This bizarre behavior pointed to dark energy, a repulsive energy permeating empty space. Together, these two invisible components dominate the cosmos, with dark matter acting like cosmic glue, holding galaxies together while dark energy drives them apart. What's truly humbling is how little we actually know about them. Dark matter's particles have never been directly detected, and dark energy remains a mathematical placeholder for an effect we don't fully understand. Yet without them, the CMB's patterns wouldn't make sense. Imagine baking a cake where 95% of the ingredients are invisible. You'd only know they existed by the way the batter behaved. That's precisely how cosmologists use the CMB, as a cosmic recipe book decoding the universe's hidden ingredients through their gravitational fingerprints. This revelation reshaped our entire understanding of reality. For centuries, we assumed the universe was made of what we could see. Now, we know it's just the tip of the iceberg, with dark matter and dark energy orchestrating the grandest scales of existence. The CMB didn't just illuminate the past, it exposed the vast, uncharted frontiers of physics, reminding us that the cosmos is far stranger and more wondrous than we ever imagined. One of the most remarkable features of the cosmic microwave background is its spectrum, an almost perfect match to what physicists call a blackbody. This might sound technical, but think of a blackbody as nature's most efficient light emitter, an object that absorbs all radiation hitting it and re-emits energy in a very specific, predictable pattern. The Sun behaves like a blackbody, so does a hot iron bar glowing red. But unlike these objects, the CMB isn't just closed to a blackbody. It's the most flawless example ever observed in nature, with a spectrum so precise it defies coincidence. When scientists first detected this ancient light, its spectrum fit the blackbody curve with astonishing accuracy, down to tiny fractions of a degree. This wasn't just a minor detail, it was a smoking gun for the Big Bang. Here's why. In the early universe, everything was packed into a seething, opaque plasma where particles constantly collided, creating an environment so chaotic and dense that it behaved like an ideal blackbody. As the universe expanded and cooled, that perfectly tuned radiation was preserved, frozen into the fabric of space. The brilliance of this discovery lies in its specificity. Other cosmic phenomena, like starlight or interstellar dust, produce messy, irregular spectra, but the CMB's pristine blackbody curve points to a single, explosive origin, a moment when the entire universe was hot, dense, and uniform enough to create such a flawless imprint. It's like finding a fingerprint at a crime scene that matches only one suspect, the Big Bang itself. What's even more striking is how this perfection holds up across the entire sky. No matter where astronomers look, the CMB spectrum remains uncannily consistent, varying by less than 1 part in 10,000. This uniformity is a testament to how smoothly matter and energy were distributed in those first moments. If the universe had clumped or rippled too much early on, those imperfections would have warped the spectrum we see today. Instead, it's as if the cosmos left us a meticulously calibrated time capsule, its contents untouched by time. Modern instruments like the COBE satellite, which first measured the CMB's spectrum with precision in the 1990s, revealed just how perfectly it aligns with theory. The data points fell so exactly on the predicted curve that researchers joked it was too good, as if the universe were playing a trick on them. But that perfection is precisely what makes the CMB such a powerful tool. It's not just light, it's a cosmic barometer, a snapshot of conditions so precise that any deviation from the blackbody spectrum would force us to rethink our understanding of the universe's birth. And yet, even in this near-flawless glow, there are whispers of something deeper. The slightest deviations measured by satellites like Planck hint at physics beyond our current models, perhaps new particles, extra dimensions, or echoes of the universe's violent infancy. The CMB's spectrum isn't just a relic, it's a living puzzle, one that keeps challenging us to look closer, dig deeper, and ask what other secrets this ancient light might still be hiding. Those seemingly insignificant wiggles in the cosmic microwave background, temperature differences barely noticeable at 1 part in 100,000, are anything but random noise. They're the universe's first brushstrokes, the delicate imprints that grew into galaxies, stars, and everything we know today. Imagine blowing up a balloon with faint pencil marks on its surface. As the balloon expands, those tiny marks stretch into vast patterns. That's exactly what happened with the CMB's temperature fluctuations. What began as quantum ripples, smaller than subatomic particles in the fiery aftermath of the Big Bang, were inflated to cosmic proportions during the universe's explosive early growth spurt, leaving behind a frozen record of density variations. These minuscule hot and cold spots, some regions slightly denser, others more sparse, became the gravitational anchors for all future structure. Where matter was marginally denser, gravity had a stronger grip, pulling in nearby gas and dust over billions of years until galaxies coalesced. The cooler patches, meanwhile, evolved into the vast cosmic voids we see today, empty stretches where matter was too thin to clump together. It's staggering to think that the grand tapestry of the universe, spiral galaxies, swirling nebulae, even our own Milky Way, traces back to these infinitesimal whispers in the ancient light. But how do we know this isn't just speculation? The evidence is etched into the CMB's statistical patterns. When scientists map these temperature variations, they don't see chaos, they see peaks and valleys in precise mathematical arrangements, like the harmonics of a cosmic symphony. The spacing between these peaks reveals critical details: the universe's curvature, the amount of ordinary matter, even the pull of dark matter. For instance, the first major peak tells us the universe is geometrically flat, while the second and third peaks confirm the ratio of normal matter to dark matter. It's as if the universe left us a carefully coded message in the CMB's fluctuations, one that's taken decades to decipher. What's even more mind-bending is the scale of these fluctuations. The largest structures we see today, superclusters of galaxies spanning hundreds of millions of light-years, arose from seeds just 1 part in 10,000 denser than their surroundings. That's like predicting a mountain range from a grain of sand. Yet over cosmic time, gravity amplified these tiny differences, sculpting the universe into the intricate web we observe now. Without those initial imperfections, space would have remained a featureless void with no stars, no planets, and no life to ponder its origins. The CMB's temperature map is more than a snapshot, it's a living blueprint. By studying it, cosmologists have reconstructed the universe's growth like detectives piecing together a crime scene. They've simulated how those primordial density fluctuations evolved, matching computer models to observed galaxy distributions with uncanny accuracy. And the story isn't over. New telescopes like the Simons Observatory are probing these fluctuations with even finer precision, hunting for clues about inflation, dark energy, and the universe's ultimate fate. So the next time someone dismisses something as just background noise, remember, the faintest whispers can hold the loudest truths. In the case of the CMB, a fraction of a degree's difference shaped the destiny of the cosmos, proving that sometimes the smallest things cast the longest shadows. One of the most mind-bending revelations from the cosmic microwave background is this: the universe we inhabit isn't curved like a sphere or warped like a saddle. It's astonishingly, impeccably flat. Not flat in the everyday sense like a tabletop, but flat in cosmic terms, meaning parallel lines will never meet or diverge no matter how far they travel across the fabric of space. This isn't just a theoretical guess, it's written plainly in the CMB's temperature patterns, etched into the ancient light like a cosmic surveyor's measurement. To understand how this works, picture throwing a rock into a pond. The ripples spread outward in perfect circles if the pond is flat. But if the pond were curved like a sphere, those ripples would eventually converge or diverge in predictable ways. The CMB acts like those ripples, but on a universal scale. When scientists mapped its temperature fluctuations, they weren't just looking at random hot and cold spots, they were measuring the geometry of space itself. The spacing between those fluctuations revealed something extraordinary. The universe's large-scale curvature is zero within a razor-thin margin of error. This flatness has profound implications. For decades, cosmologists debated whether the universe was open, curved outward like a saddle, destined to expand forever, closed, curved inward like a sphere, eventually collapsing back on itself, or perfectly balanced between the two. The CMB settled the argument. Those tiny temperature variations matched predictions for a flat universe so precisely that there's no realistic wiggle room. Space isn't just approximately flat, it's flat to within 1%. But here's the puzzle. A perfectly flat universe requires an unbelievable fine-tuning of matter and energy. Too much mass and space would curve inward. Too little and it would curve outward. For the universe to be this flat after billions of years of expansion, its initial conditions had to be balanced on a knife's edge, a 1 in a trillion coincidence unless something extraordinary happened. That something is cosmic inflation, the theory that the universe underwent a blistering exponential expansion in its first fraction of a second, stretching any primordial curvature so thin that it became negligible. Inflation didn't just predict flatness, it demanded it, turning a fine-tuning mystery into a natural consequence of physics. The CMB's flatness isn't just a curiosity, it's a cornerstone of modern cosmology. It tells us the universe's total energy density is exactly balanced, a cosmic tightrope walk between expansion and gravity, and it hints at deeper mysteries like dark energy's role in maintaining that balance over time. Without this flatness, galaxies might never have formed, and the cosmos could have collapsed or torn apart long before life arose. So when we say the universe is flat, we're not just describing its shape, we're reading the signature of its birth, a secret kept for 14 billion years and whispered to us through the oldest light there is. The light we now detect as the cosmic microwave background didn't always glow in the microwave range. 13.8 billion years ago, it blazed across the universe as searing visible light, a brilliant, blinding flash hotter than the surface of any star. But as space itself stretched over eons, that light stretched with it, its wavelength elongating like taffy pulled thin. Today, those once fiery photons have been redshifted so dramatically that they've cooled to just 2.7 degrees above absolute zero, fading into the microwave spectrum. This shift isn't just a curious detail, it's one of the most vivid pieces of evidence we have for the universe's relentless expansion. Picture a firework exploding in the night sky. At first, its light is intense and white-hot, but as the embers fly outward, they cool, fading from blue to yellow to red. The CMB has undergone a similar transformation, but on a cosmic scale. When it was first emitted, around 380,000 years after the Big Bang, the universe was a scorching plasma, glowing at roughly 3,000 degrees Kelvin. Its light would have appeared as an orange-white radiance, like the filament of an incandescent bulb. But as the cosmos ballooned in size, the light's wavelength stretched redshifting, while its energy diluted into the cold microwave static we observe today. This extreme redshift is more than just a testament to time's passage. It's a direct measurement of how much the universe has expanded. The numbers are staggering. The CMB's light has stretched by a factor of about 1,100, meaning space itself has grown over 1,000 times larger since that primordial glow broke free. To put that in perspective, if you could rewind cosmic history, compressing the universe back to its original size, the CMB's microwaves would snap back into visible light, a blinding cosmic dawn illuminating an infant cosmos. What's even more remarkable is how precisely this redshift aligns with other evidence for cosmic expansion. Distant galaxies show redshifted light too, their spectral lines shifted toward longer wavelengths as they race away from us. But while galactic redshifts vary depending on distance, the CMB's redshift is uniform, a single, all-encompassing fingerprint of space stretching everywhere at once. It's the ultimate calibration tool, a universal yardstick confirming that expansion isn't just happening in isolated pockets, but is woven into the very fabric of reality. And yet, this extreme stretching holds another secret. The CMB's redshift isn't just a relic of the past, it's still happening. Right now, as you watch this, the universe continues to expand, and the CMB's light is redshifting further. Billions of years from now, future astronomers, if any exist, won't detect microwaves at all. The CMB will have faded into even longer radio waves, its signal growing fainter as the cosmos accelerates toward an ever colder, ever darker future. The very act of observing this ancient light, then, is a race against time, a fleeting window into an era when the universe was young enough to still glow, and we were close enough to its birth to catch the echo before it vanishes forever. The cosmic microwave background isn't just a relic. It's a cosmic speedometer helping us measure how fast the universe is stretching apart. One of the most critical numbers in cosmology, the Hubble constant, represents this expansion rate, and the CMB provides one of the most precise ways to calculate it. But here's where things get intriguing. When scientists compare the CMB's value with other methods like tracking distant supernova or pulsating stars, the numbers don't always match. This discrepancy isn't just a minor hiccup. It's a full-blown cosmic mystery that could reshape our understanding of physics. To grasp how the CMB measures expansion, think of it like a fossilized ripple frozen in time. Those subtle temperature fluctuations we've talked about, their size and spacing act as a cosmic ruler. By analyzing how these patterns stretch across the sky, scientists can work backward to determine how quickly the universe must have expanded to produce the structures we see today. Satellites like Planck have mapped these fluctuations with such precision that the CMB-derived Hubble constant is known to within just a few percent. According to this method, the universe expands at about 67 kilometers per second for every megaparsec of space, a number that seems rock-solid based on the physics of the early universe. But then there's the twist. When astronomers measure expansion using nearby objects like Type Ia supernova or Cepheid variable stars, they get a different answer, roughly 73 kilometers per second per megaparsec. That might not sound like much, but in cosmology, even a small mismatch can signal something fundamental we're missing. This tension between early universe CMB and late universe supernova measurements has sparked heated debates. Is there an error in our observations? Could dark energy be evolving over time? Or does the universe contain some exotic particle or force we haven't discovered yet? The implications are staggering. If the discrepancy is real and not just a measurement fluke, it might mean our standard model of cosmology, the very framework we use to understand the universe's evolution, is incomplete. Some theories suggest dark energy could be growing stronger, accelerating expansion faster than predicted. Others propose that neutrinos, the ghostly particles that barely interact with matter, might have unexpected properties. There's even wilder speculation about parallel universes or hidden dimensions subtly influencing our measurements. What makes the CMB so valuable in this puzzle is its role as an independent check. Unlike supernova or star-based methods, which rely on complex distance ladders and calibration, the CMB offers a direct snapshot of the universe's infancy. Its measurements are grounded in well-tested physics, like the behavior of sound waves in the primordial plasma. That's why the tension isn't just dismissed, it's taken as a potential clue, a crack in the cosmic facade that might lead to deeper truths. And the stakes couldn't be higher. Resolving this discrepancy could unlock new physics, rewriting textbooks on everything from particle behavior to the universe's ultimate fate. Future telescopes like the Nancy Grace Roman Space Telescope aim to sharpen these measurements, narrowing the gap or perhaps widening it further, forcing us to confront an even bigger mystery. For now, the CMB remains our most reliable witness to the universe's expansion, even as it whispers tantalizing hints that there's still so much we don't understand. So the next time you hear about the Hubble tension, remember, it's not just a numbers game. It's the universe daring us to look closer, to question our assumptions, and to admit that even our best theories might only be scratching the surface of reality. Hidden within the cosmic microwave background's faint glow is another layer of secrets: polarization, a subtle twisting of light that could rewrite our understanding of the universe's first moments. Like sunlight reflecting off a lake, the CMB's light isn't just uniform. Some of it vibrates in specific directions, a phenomenon caused by the way photons scattered off electrons in the early universe. But here's what's truly groundbreaking. Tangled within those polarized patterns could be the fingerprints of gravitational waves from the universe's violent inflationary phase, a discovery that would catapult us back to a trillionth of a second after the Big Bang. Imagine dropping a pebble into a pond. The ripples spread outward, but if you look closely, you'll see they're not just up and down waves. They create tiny spirals and twists in the water's surface. The CMB's polarization works similarly. As the infant universe expanded, primordial gravitational waves, ripples in spacetime itself, tugged at the plasma, imprinting a distinctive swirling pattern called B-mode polarization onto the light. This isn't just any ripple, it's a direct echo of inflation's monumental energy, a stretch of time when the universe ballooned from smaller than a proton to the size of a grapefruit in less than a blink. Detecting these B-modes is like hunting for whispers in a hurricane. The signal is incredibly faint, buried under interference from cosmic dust and the polarized light of our own galaxy. Yet the payoff would be historic. Confirming these patterns would prove inflation happened, revealing not just how the universe expanded but what powered it, perhaps a field of exotic energy or even a glimpse of quantum gravity at work. It's like finding the signature of the cosmic architect scribbled in spacetime's own handwriting. The search has already led to dramatic moments. In 2014, the BICEP-2 team thought they'd found these primordial swirls, only to realize later that galactic dust muddied their data. But the hunt continues with projects like the Simons Array and future space telescopes, each instrument more sensitive than the last. What's remarkable is how much rides on this minuscule signal. If detected, B-modes wouldn't just confirm inflation, they'd tell us its energy scale, hinting at whether grand unification theories tying all fundamental forces together are correct. And there's another twist. The CMB's polarization isn't just about inflation. It also maps how matter clumped together over time, tracing the gravitational tug of dark matter and the push of dark energy. By separating these effects, scientists can tease apart the universe's ingredients with unprecedented precision. So when we study this polarized light, we're not just looking at a relic, we're decoding a dynamic record of cosmic evolution, written in the language of vibrating photons and warped spacetime. What's humbling is the scale of this ambition. We're trying to read perturbations smaller than 1 part in 10 million, patterns frozen into the sky when the universe was a fraction of its current age. Yet if we succeed, it would be like uncovering the first page of the cosmic story, a chapter written in gravitational waves and whispered to us across 14 billion years. Until then, the CMB's polarized light remains one of the most tantalizing puzzles in cosmology, a riddle wrapped in microwaves hidden in plain sight. The cosmic microwave background doesn't just support the Big Bang theory, it outright dismantles competing ideas about the universe's origins. Take the steady-state model, once a formidable rival to the Big Bang. Proposed in the 1940s by astronomers like Fred Hoyle, this elegant theory suggested the universe had no beginning or end. Instead of a single explosive origin, matter was continuously created to fill the gaps as space expanded, maintaining a constant density forever. It was a beautiful, eternal vision of the cosmos until the CMB's discovery blew it apart. Here's why. The steady-state model couldn't explain the CMB's existence. If the universe had no fiery beginning, where did this all-pervading microwave glow come from? Proponents scrambled to retrofit explanations, suggesting maybe it was starlight absorbed and re-emitted by cosmic dust. But that idea collapsed under scrutiny. The CMB's spectrum is a perfect blackbody, something only achievable in the extreme conditions of a hot, dense early universe. Dust-scattered starlight would produce a messy, uneven spectrum, nothing like the pristine curve we observe. Worse, the steady-state model predicted a far dimmer background signal, if any at all. The CMB's intensity was a death knell, proving the universe was once unimaginably hotter and denser, exactly what the Big Bang predicted. Then there's the clincher, the CMB's fluctuations. In a steady-state universe, matter distribution should be smooth on large scales, with no need for primordial density variations. Yet the CMB's temperature map is a patchwork of hot and cold spots, the seeds of future galaxies. These fluctuations align perfectly with the Big Bang's narrative, an expanding universe where gravity amplifies tiny initial irregularities over time. No amount of tweaking could make the steady-state model account for this intricate cosmic blueprint. Other alternative cosmologies met similar fates. The tired light hypothesis, which proposed that light loses energy over vast distances instead of space expanding, couldn't reproduce the CMB's blackbody spectrum or its polarization patterns. Even more exotic ideas like plasma cosmology or cyclical models stumbled when confronted with the CMB's precise measurements. Each failed test underscored the same truth. The Big Bang wasn't just one theory among many. It was the only framework that could explain the universe's oldest light in all its detail. What's striking is how decisively the CMB settled this debate. Science rarely offers clean, unequivocal answers, but here the evidence was overwhelming. The steady-state model's proponents, including Hoyle himself, eventually conceded that the CMB left no room for their theory. It was a rare moment in scientific history where a single discovery didn't just shift the consensus, it rewrote the rules entirely. The CMB didn't just confirm the Big Bang, it turned competing ideas into footnotes, proving that sometimes the universe leaves us clues so clear they're impossible to ignore. Before we could decode the cosmic microwave background's secrets, we needed a clear map, a way to see its faint patterns across the entire sky. That breakthrough came in 1989 with NASA Cosmic Background Explorer, or COBE, a mission so precise it didn't just observe the CMB, it transformed our understanding of the universe's infancy. COBE instruments were designed to measure the faintest whispers of microwave radiation with unprecedented accuracy, and what they found was nothing short of revelatory. For the first time, humanity had a full sky portrait of the universe's oldest light, revealing temperature variations so subtle they'd gone undetected for decades. The significance of this achievement can't be overstated. COBE maps confirmed two critical predictions of the Big Bang theory with stunning clarity. First, the CMB's spectrum matched a perfect blackbody curve, just as theorists had expected from the afterglow of a hot, dense early universe. Second, the satellite detected those tiny temperature fluctuations, hot and cold spots differing by mere millionths of a degree, proving the primordial universe wasn't perfectly smooth. These minuscule variations were the gravitational seeds that would eventually grow into galaxies and galaxy clusters, solving one of cosmology's biggest puzzles: how structure emerged from uniformity. What made COBE extraordinary wasn't just its findings, but how it achieved them. The satellite's instruments had to be cooled to near absolute zero to avoid interference from their own heat, and its measurements were so delicate that scientists spent years verifying the data. When the team finally unveiled the results, the scientific community erupted. The COBE map showed a universe that was almost perfectly uniform, but with just enough variation to explain everything we see today. It was like discovering the brushstrokes on a masterpiece we'd only seen from a distance. The mission's legacy extends far beyond its initial discoveries. COBE laid the groundwork for every CMB experiment that followed, from WMAP to Planck, refining our measurements and sharpening our cosmic timeline. Its success was so monumental that its lead scientists, John Mather and George Smoot, received the Nobel Prize in Physics in 2006, a rare honor for an observational mission. But perhaps COBE's greatest triumph was turning the CMB from a theoretical curiosity into a cornerstone of modern cosmology, proving that even the faintest light can illuminate the grandest truths. What's often overlooked is how close this revolution came to never happening. COBE launch was nearly derailed by the Challenger disaster, which grounded NASA's shuttle fleet and forced engineers to reconfigure the satellite for a Delta rocket at the last minute. Had those delays lasted much longer, the mission might have lost funding entirely. Instead, COBE not only launched but exceeded every expectation, gifting us a window into the universe's first moments and setting a new standard for precision cosmology. Its story is a testament to perseverance, both human and cosmic, reminding us that sometimes the most profound discoveries hinge on the thinnest margins of luck, timing, and sheer determination. If COBE gave us our first clear snapshot of the cosmic microwave background, then WMAP, the Wilkinson Microwave Anisotropy Probe, turned that snapshot into an ultra-high-definition portrait. Launched in 2001, this spacecraft wasn't just an upgrade. It was a revolution in precision, measuring temperature fluctuations in the CMB with a sensitivity 50 times sharper than COBE. Where COBE saw whispers, WMAP heard full sentences, transforming blurry cosmic hints into crystal-clear data that would redefine our place in the universe. What set WMAP apart was its vantage point, a graceful orbit around the second Lagrange point, 1,000,000 miles from Earth, where interference from our planet's heat and radio noise couldn't muddy the signals. From this serene outpost, its instruments mapped the CMB's subtle temperature differences down to millionths of a degree, revealing patterns so intricate they looked like cosmic fingerprints. These weren't just minor improvements, they were quantum leaps. WMAP data allowed scientists to calculate the universe's age with unprecedented accuracy, 13.7 billion years, give or take just 1%. It pinned down the composition of the cosmos: 5% ordinary matter, 25% dark matter, and 70% dark energy, numbers so precise they became the bedrock of modern cosmology. But WMAP's real magic lay in the details. Its maps exposed the CMB's acoustic peaks, frozen ripples from pressure waves that reverberated through the primordial plasma like echoes in a cosmic canyon. The spacing of these peaks revealed the universe's geometry with certainty. Space is flat, just as inflation theory predicted. Even more astonishing, WMAP data hinted at the universe's ultimate fate, suggesting dark energy would keep accelerating expansion forever, leading to a cold, lonely end rather than a dramatic collapse. The mission also tackled lingering mysteries. By measuring how light from the CMB polarized as it interacted with matter, WMAP traced the distribution of dark matter across the early universe, confirming its gravitational pull shaped galaxies long before stars ignited. It even detected a puzzling axis of evil, an unexpected alignment of temperature fluctuations that some theorists speculate could hint at pre-Big Bang physics or exotic large-scale structures beyond our current understanding. What's often forgotten is how WMAP legacy rippled far beyond academia. Its findings settled decades-long debates, like whether the universe would eventually recollapse, it won't, or if dark energy was just a fluke, it's very real. The mission's data became the gold standard, cited in thousands of papers and textbooks, while its team, led by Nobel laureate John Mather's protege, Charles Bennett, proved that sometimes the quietest instruments shout the loudest truth. Looking back, WMAP didn't just refine COBE work, it turned cosmology from a field of speculation into a precision science. Its maps were so definitive that when the even more sensitive Planck satellite launched years later, its role wasn't to contradict WMAP but to refine its numbers by a hair's breadth. That's the mark of a landmark mission, when later explorers don't rewrite your story, they just add footnotes, and in the case of WMAP, those footnotes were written in the language of the universe itself, etched into microwaves that had traveled since the dawn of time. If WMAP gave us high definition, then Planck handed us an IMAX-worthy masterpiece of the cosmic microwave background. Launched in 2009 by the European Space Agency, this satellite wasn't just an incremental upgrade, it was a quantum leap in precision, capturing the CMB's faint whispers with such clarity that it felt like wiping cosmic dust off an ancient fresco. For 4 years, Planck's instruments cooled to just 1/10 of a degree above absolute zero. scanned the sky with a sensitivity 10 times sharper than WMAP, measuring temperature variations so minute they'd be like detecting a single snowflake's weight on a continent. What emerged from its data was nothing short of breathtaking. Planck's all-sky map revealed the CMB's temperature fluctuations down to millionths of a degree, a level of detail that exposed textures no one had seen before. But the real shock wasn't just the precision, it was the anomalies. Like a detective spotting irregularities in a seemingly perfect alibi, Planck uncovered quirks in the CMB that defied expectations. For starters, one hemisphere of the universe appeared slightly warmer than the other, a so-called axis of evil that clashed with the assumption of cosmic uniformity. Then there were the unnervingly large cold spots, regions so vast and unexplained that some theorists wondered if they were bruises from a collision with another universe. Planck's measurements didn't just refine numbers, they redrew boundaries. The universe's age was tweaked to 13.8 billion years, its expansion rate recalibrated, and its composition fine-tuned to include even more dark energy than previously thought. But perhaps its most tantalizing gift was the tightening of cosmic inflation's timeline. By analyzing the CMB's polarization patterns, Planck narrowed the window for when inflation occurred to a sliver of a second after the Big Bang, offering the strongest evidence yet that space once expanded faster than light itself. Yet for all its triumphs, Planck left us with more questions than answers. Those anomalies it uncovered, they still defied tidy explanations, haunting cosmology like cosmic ghosts. Some researchers argue they're statistical flukes, while others whisper about new physics, extra dimensions, exotic dark matter interactions, or even remnants of a universe that existed before ours. Whatever the truth, Planck's legacy isn't just in the answers it provided, but the mysteries it etched into the sky, reminding us that even our sharpest tools can't yet pierce all of creation's veils. What's remarkable is how much this mission reshaped our cosmic narrative with quiet persistence. Unlike flashy telescopes that capture colorful nebulae, Planck worked in the frigid shadows, its detectors tracing patterns invisible to human eyes. And when its coolant finally ran out in 2013, it didn't just fade away. It handed us a cosmic puzzle box, its contents still being unlocked by theorists a decade later. That's the mark of a great explorer, not just the maps it leaves behind, but the uncharted territories it dares us to explore. Among the cosmic microwave background's tapestry of hot and cold spots, one anomaly stands out like a cosmic sore thumb, the infamous cold spot. Stretching nearly 2 billion light-years across, this region is significantly colder than its surroundings, a bizarre deviation that defies standard cosmological models. At first glance, it might seem like just another statistical fluke in the ancient light, but the cold spot's scale and significance have sparked wild theories, from parallel universes bumping into ours to exotic defects in the very fabric of spacetime. To grasp why this feature is so puzzling, think of the CMB's temperature variations like ripples on a pond. Most are small, the result of random quantum fluctuations stretched by cosmic inflation. But the cold spot is more like a sudden, unexplained crater. Its sheer size and depth shouldn't exist if the universe evolved as smoothly as our models suggest. When scientists first spotted it in WMAP data, they assumed it was noise, but Planck's sharper measurements confirmed it was real, and worse, it refused to vanish under scrutiny. One leading explanation involves a cosmic void, an enormous, underdense region of space where matter is unusually sparse. If such a void existed between us and the cold spot, light passing through it would lose energy due to the universe's expansion, a phenomenon called the integrated Sachs-Wolf effect. The problem, a void large and empty enough to explain the cold spot, would itself be astronomically improbable, like finding a hole in the ocean deeper than Everest is tall. Then there's the far wilder possibility. The cold spot could be a bruise from a collision with another universe. In the multiverse theory, our cosmos might be one bubble among countless others in an eternally inflating spacetime foam. If a neighboring bubble universe grazed ours long ago, the energy of that collision could have left a mark, a cold imprint in the CMB. It's a speculative idea, but not impossible. After all, if the multiverse exists, such scars might be the only way to detect it. Yet another hypothesis invokes cosmic textures, knots in spacetime formed during phase transitions in the early universe, like cracks in ice as it freezes. These defects, if they exist, could warp light in ways that mimic the cold spot's profile. The challenge: no one's ever observed a cosmic texture, and their existence hinges on untested physics. What makes the cold spot so tantalizing is that it straddles the line between anomaly and discovery. It could be a statistical mirage, a trick of cosmic variance. Or it could be the first crack in our understanding, hinting at physics beyond the standard model, extra dimensions, exotic fields, or even evidence for theories we haven't dreamed up yet. For now, it remains one of the CMB's greatest unsolved puzzles, a silent question mark written in microwaves. And until we peer deeper into the cosmos with future telescopes, the cold spot will keep challenging us to wonder: is it a flaw in our maps or a signpost to something far stranger? The cosmic microwave background's temperature, 2.7 Kelvin, isn't just a random number. It's a cosmic fingerprint, a precise measurement that confirms one of the most dramatic transformations in the universe's history. To understand why this number matters, picture the early cosmos as a scorching inferno, hotter than the core of any star, packed with particles and radiation colliding furiously. Then, as space expanded and cooled, the universe reached a critical threshold, around 3000 degrees Kelvin, cool enough for electrons and protons to finally combine into neutral hydrogen atoms. At that moment, light broke free from the plasma, streaming outward in all directions. But here's the key: that light didn't stay blazing hot. Over billions of years, the stretching of space itself stretched the light's wavelengths, sapping its energy and cooling it down to the faint microwave whisper we detect today. This cooling follows a predictable cosmic recipe. When light gets redshifted, stretched by the expansion of the universe, its energy drops, and so does its temperature. Back in the 1940s, physicists like George Gamow calculated that if the Big Bang had happened, the leftover radiation should have cooled to just a few degrees above absolute zero by now. Their prediction, between 5 and 10 Kelvin, later refinements narrowed it to around 3 Kelvin, astonishingly close to the 2.7 Kelvin we actually observe. That's less than 3 degrees above the coldest possible temperature in nature, a frigid relic of a universe that once glowed white-hot. What's remarkable is how this temperature reveals the universe's expansion history. Every photon in the CMB has been traveling for 13.8 billion years, and during that time, space has stretched by a factor of about 1,100. That expansion didn't just increase distances, it stretched the light itself, diluting its energy by the same amount. If you rewind the math, that means the CMB's light, now microwaves at 2.7 Kelvin, was once visible light at 3000 Kelvin, glowing like the surface of a red-hot star. But the precision of this temperature is what seals the deal. The CMB's spectrum matches a perfect blackbody curve, the hallmark of thermal equilibrium in the early universe's dense plasma. Alternative theories like the steady-state model couldn't explain such a perfect match. Only the Big Bang's fiery beginning and subsequent cooling could produce this exact thermal fingerprint. It's as if the universe left us a receipt stamped with the temperature it had when light first escaped, then meticulously tracked its cooling over eons. And here's the poetic part: 2.7 Kelvin isn't just a relic. It's a benchmark. It tells us how much the universe has expanded, how much energy has been lost to that expansion, and even hints at the nature of dark energy which now dominates the cosmos. Future measurements might reveal even subtler variations, but for now, This number stands as one of the most precise validations of our cosmic story, a cold echo of the universe's fiery birth. Hidden within the cosmic microwave background is a kind of cosmic symphony, an echo of sound waves that rippled through the newborn universe like the deep notes of a colossal bass drum. These aren't sound waves as we know them today. In the searing plasma of the early cosmos, dense regions of matter acted like pressure chambers, where gravity pulled material inward while radiation pressure pushed outward, creating oscillations that traveled at nearly 2/3 the speed of light. Over hundreds of thousands of years, these waves surged and receded, leaving behind a frozen record in the CMB's temperature patterns, a snapshot of the universe's first and only musical performance. Think of it like dropping a stone into a pond. The initial splash creates waves that spread outward, but if the pond suddenly froze solid, those ripples would be preserved in the ice. The CMB works the same way. When the universe cooled enough for atoms to form, releasing light from the plasma's grip, those primordial sound waves were instantly frozen into the fabric of space, imprinting their peaks and troughs as subtle hot and cold spots in the microwave sky. Today, we see them as concentric rings in the CMB's temperature map, with each ring representing a different harmonic of the cosmic scale. What's astonishing is the scale of these oscillations. The distance between peaks in the CMB's patterns corresponds to the farthest a sound wave could travel before the universe became transparent, about 450,000 light-years at that time. Known as the sound horizon, this measurement acts like a cosmic yardstick, allowing scientists to calculate fundamental properties of the universe with breathtaking precision. The spacing between these acoustic peaks reveals the curvature of space, the density of matter, even the push of dark energy, all encoded in vibrations from an era before stars or galaxies existed. And just like musical notes, these oscillations had harmonics. The first peak in the CMB's power spectrum tells us about the universe's overall geometry, confirming it's flat. The second peak reveals the amount of ordinary matter, while the third and later peaks expose the gravitational tug of dark matter. It's as if the early universe composed a symphony where each instrument's note carried information about a different cosmic ingredient, waiting 14 billion years for us to listen. Perhaps most remarkably, these sound waves didn't just fade into silence, they sculpted the universe. The overdense regions where waves peaked became the seeds for galaxies, while the underdense troughs evolved into today's vast cosmic voids. Every cluster of galaxies, every filament of the cosmic web, traces back to these primordial vibrations. In a very real sense, we're seeing the universe's first and most consequential rhythm, a beat that set the tempo for all of cosmic history. So when astronomers study these patterns, they're not just analyzing ancient light, they're eavesdropping on the soundtrack of creation itself. The CMB music might be silent now, stretched into microwaves by time's unrelenting expansion, but its melody still resonates through the structure of everything we see. And like any great composition, the more closely we listen, the more secrets it reveals. Locked within the cosmic microwave background's faint glow is a kind of cosmic clock, one that ticks not in seconds or years, but in billions of them. For decades, astronomers debated the universe's age, with estimates swinging wildly based on conflicting measurements of distant stars and galaxies. But the CMB changed everything, offering a definitive answer written in microwaves, 13.8 billion years, precise to within just 1%. How did this ancient light become the ultimate timekeeper? The secret lies in the way it captures the universe's earliest moments with near-perfect fidelity. Picture the CMB as a frozen frame from a cosmic film strip, preserving the universe's state just 380,000 years after the Big Bang. By analyzing the precise spacing of its temperature fluctuations, those subtle hot and cold spots, scientists can rewind the expansion of space itself, calculating backward to determine exactly when the universe began. It's like measuring the ripples in a pond after a stone was thrown and using their spacing to deduce the exact moment the stone hit the water. The key is the CMB's acoustic peaks, patterns that reveal how fast the infant cosmos expanded and how much matter and energy it contained. These peaks act as cosmic mile markers, letting us triangulate the universe's age with astonishing precision. But the real breakthrough came when satellites like WMAP and Planck mapped these patterns across the entire sky. Their data didn't just suggest an age, they pinned it down by measuring the universe's geometry. A closed universe would curve inward, recollapsing before reaching 13.8 billion years. An open one would expand too quickly, making it older. Instead, the CMB revealed a Goldilocks scenario, a perfectly flat universe where expansion and gravity balanced just enough to yield that exact, elegant number. What's remarkable is how many independent lines of evidence now converge on this figure. The CMB's age prediction aligns with measurements from ancient star clusters, the decay of radioactive elements in meteorites, and even the motions of distant galaxies. It's as if the universe left us multiple clocks, all synchronized to the same cosmic hour. And while future observations might tweak the decimal points, the CMB's verdict is clear. We live in a 13.8 billion-year-old universe, one that's left its birth certificate written in microwaves for anyone patient enough to read it. Yet this number isn't just trivia, it's a cornerstone of cosmology. Knowing the universe's age tells us how long stars have had to forge heavy elements, how much time galaxies needed to assemble, and even how long life might have had to emerge. The CMB didn't just give us a number, it gave us a timeline, a way to anchor every cosmic event from the first atoms to the birth of our own solar system. And buried in that timeline might be clues to deeper mysteries, like why the universe's expansion is accelerating or what came before the Big Bang. For now, though, 13.8 billion years stands as our most reliable answer, etched into the oldest light there is. The cosmic microwave background doesn't just tell us about the universe's infancy, it holds clues to its very first split second of existence, a period so brief and violent that it defies imagination. This is the era of cosmic inflation, a theory proposing that the universe underwent an exponential growth spurt, ballooning from smaller than a proton to the size of a grapefruit in less than a trillionth of a second. What's astonishing is that the CMB's delicate patterns, its near-perfect uniformity punctuated by tiny fluctuations, serve as the strongest evidence we have that this surreal expansion actually happened. Let's break this down. The CMB's uniformity is its most striking feature. No matter where you look in the sky, the temperature varies by less than 1 part in 100,000, a level of smoothness that seems impossible unless the universe underwent a dramatic smoothing process early on. Think of it like stretching a crumpled sheet of paper until every wrinkle vanishes. Inflation did precisely that to space itself, ironing out irregularities by expanding the cosmos so rapidly that any initial lumps or curves became cosmically insignificant. Without inflation, there's no plausible way to explain why regions of the universe now separated by billions of light-years regions that could never have exchanged heat or information share almost identical temperatures. They were simply too far apart for light to have connected them in the time available. But inflation's signature isn't just in the CMB's smoothness, it's also in the subtle imperfections. Quantum mechanics tells us that empty space is never perfectly still. It's a seething froth of tiny fluctuations. During inflation, these microscopic quantum ripples were stretched to cosmic proportions, imprinting faint density variations onto the fabric of spacetime. These variations later became the seeds for the CMB's hot and cold spots, and ultimately the galaxies and voids we see today. The CMB's fluctuation patterns match inflation's predictions with uncanny precision, like finding a fingerprint that could only belong to one suspect. What's even more compelling is the spectrum of these fluctuations. Inflation doesn't just predict that there should be variations, it forecasts their exact distribution across different scales, a pattern called the scale invariant spectrum. When scientists analyzed the CMB's temperature map, they found that its fluctuations followed this predicted spectrum almost perfectly, a triumph for inflationary theory. It's as if the universe left us a detailed receipt, itemizing the conditions of its own explosive birth. Yet inflation's echoes go even deeper. The theory also predicts the existence of primordial gravitational waves, ripples in space-time generated by inflation's violent expansion. While these waves haven't been definitively detected in the CMB's polarization patterns yet, their discovery would be the smoking gun confirming inflation beyond doubt. Even without them, the CMB's uniformity and fluctuation patterns make inflation the only theory that can explain the universe's large-scale structure without resorting to impossible coincidences. The beauty of this evidence lies in its simplicity. The CMB doesn't just support inflation, it demands it. Without that frenzied early growth spurt, the universe would look wildly different, less uniform, less flat, and far less hospitable to the intricate structures that eventually gave rise to stars, planets, and us. So when we study those faint microwaves, we're not just glimpsing the aftermath of the Big Bang, we're peering back to the moment when the very fabric of reality decided, in a flash, what kind of universe we would inherit. And that's a fact written in light older than stars themselves. The cosmic microwave background might be more than just a relic, it could be our first glimpse into dimensions beyond our own. Hidden within its subtle anomalies and puzzling fluctuations are faint whispers that some physicists believe might reveal the existence of higher dimensions, realms of reality folded so tightly they escape ordinary detection. Imagine space as a vast sheet of paper. We experience only its flat surface, but what if tiny, crumpled dimensions existed at scales too small to see, influencing gravity, light, and even the very fabric of the early universe? The CMB's temperature patterns and polarization signals could be bearing the fingerprints of these hidden dimensions, warping spacetime in ways that leave barely perceptible imprints in the ancient light. One of the most tantalizing hints comes from the so-called power asymmetry, the observation that one hemisphere of the CMB appears slightly warmer than the other, a deviation that standard cosmology struggles to explain. Some theorists suggest this lopsidedness could arise from gravitational leakage, where our three-dimensional universe brushes against a higher dimensional space, altering the distribution of energy in ways that skew the CMB's uniformity. It's like detecting the shadow of an unseen object cast on a wall. We can't see the extra dimensions directly, but their influence might be etched into the microwave sky. Then there's the cold spot, that enigmatic region of the CMB that's colder than it should be. While some attribute it to a cosmic void or statistical fluke, others wonder if it could mark the collision of our universe with another in a higher dimensional, bulk space, like ripples from a pebble dropped into a pond we can't see. String theory, which posits up to 11 dimensions, provides a framework for such ideas, suggesting that the CMB's anomalies might be signatures of brain's multidimensional membranes interacting in ways that leave traces in our observable universe. Even the CMB's polarization patterns could hold clues. Certain twisting swirls in the light's orientation, known as B modes, might not just stem from primordial gravitational waves but from exotic particles or fields tied to extra dimensions. If future telescopes detect B modes with characteristics that defy conventional explanations, it could point to physics beyond the standard model, where higher dimensions play a role in shaping the cosmos. What makes these ideas so compelling is their audacity. The CMB, already a window into the universe's infancy, might also be a lens focused on realities we've yet to imagine. While definitive proof remains elusive, the mere possibility transforms the microwave sky from a static snapshot into a dynamic puzzle, one where every irregularity could be a cipher waiting to be decoded. Whether these anomalies stem from extra dimensions, parallel universes, or something even stranger, the CMB continues to challenge us with its quiet, persistent mysteries, reminding us that the universe's oldest light might still have its most revolutionary stories to tell. Every photon of the cosmic microwave background you've ever heard about, whether in a documentary, a textbook, or even the static on an old TV, has been on an unimaginable journey. These particles of light have traveled for over 13 billion years, racing across an ever-expanding universe to reach us at this exact moment. To put that into perspective, when this light first broke free, our galaxy didn't exist. Stars as we know them hadn't even formed. The universe was a swirling, opaque fog of plasma, so dense that light couldn't travel more than a fraction of an inch before being absorbed and re-emitted. Then, in a cosmic blink, everything changed. Around 380,000 years after the Big Bang, the universe finally cooled enough for electrons and protons to combine into neutral hydrogen atoms, a pivotal moment called recombination. Suddenly, space became transparent, and light that had been trapped in the chaotic plasma burst free for the first time. That flash of light, once blazing hot, has been traveling ever since, stretched and cooled by the relentless expansion of space into the faint microwaves we detect today. It's not just light, it's a time capsule carrying pristine information about the universe's infancy, untouched by the chaos of stars, galaxies, or black holes that would come later. What's staggering is the sheer fidelity of this signal. Over its 13 billion-year voyage, the CMB's light has crossed unfathomable distances, passing through galaxy clusters, dark matter halos, and vast cosmic voids. Yet it arrives almost exactly as it left, its patterns barely disturbed. That's because most of space is, well, space so empty that photons rarely bump into anything. Even when they do, the interactions are subtle, leaving faint scars like the Sunyaev-Zeldovich effect, where galaxy clusters slightly distort the CMB's temperature. These distortions aren't noise, they're clues, helping astronomers map the distribution of matter across cosmic time. But here's what's even more mind-bending. The light we're detecting now is just reaching us after its marathon journey. In a very real sense, when we look at the CMB, we're not seeing the universe as it is today, we're seeing it as it was before the first stars ignited. It's like finding a letter mailed at the dawn of time, its contents preserved perfectly, detailing a world that no longer exists. And because light takes time to travel, the CMB acts as a spherical shell around us, a surface of last scattering that marks the edge of the observable universe. Beyond that, we can't see because light from those regions hasn't had time to reach us yet. This ancient light doesn't just connect us to the past, it shapes our understanding of the present. By measuring how the CMB's photons have been stretched and dimmed over time, scientists can calculate the universe's expansion history with startling precision. It's like cosmic archaeology, where every photon is an artifact, its wavelength a fingerprint of how much space has stretched since the moment it was set free. Future telescopes will probe even finer details, but for now, the CMB remains our clearest snapshot of the universe's first breath, a beacon from an era when everything was simpler, hotter, and filled with the raw potential of creation. Einstein's theory of general relativity has passed every test we've thrown at it, from bending starlight around the sun to keeping GPS satellites accurate. But the cosmic microwave background offers something even more extraordinary, a way to test relativity not just in our solar system or galaxy, but across the entire observable universe. This ancient light acts like a colossal physics lab, letting us probe gravity's grip on scales so vast they dwarf anything we can simulate on Earth. One of relativity's boldest predictions is that massive objects warp spacetime, bending the path of light as it travels. Normally, we see this effect in isolated cases, like a distant quasar's light curving around a galaxy. But the CMB shows this phenomenon playing out on a cosmic stage. As its photons journeyed toward us for billions of years, they passed through countless galaxy clusters and dark matter halos, each one subtly deflecting the light's path like a lens. These distortions, called gravitational lensing, imprint faint swirls and smudges on the CMB's polarization patterns. By mapping these twists, astronomers can measure how much matter, both visible and dark, lies between us and the CMB, and how precisely it matches relativity's predictions. Even more striking is how the CMB tests relativity's vision of cosmic expansion. Einstein's equations describe how space itself stretches, but they leave room for surprises, like dark energy's acceleration. The CMB's temperature fluctuations act as a yardstick for this expansion. Their patterns reveal how quickly the universe grew after the Big Bang and how that growth changed over time. When combined with supernova data, the CMB confirms that relativity holds up spectacularly well, even as dark energy dominates the cosmos. But it also leaves room for questions. Why does the universe's expansion rate measured from the CMB slightly disagree with local measurements? Could there be subtle cracks in relativity's framework, or is new physics lurking in these discrepancies? Then there's the Sachs-Wolf effect, a direct imprint of relativity on the CMB. As photons climb out of the gravitational wells of galaxy clusters, they lose energy, creating cold spots in the microwave sky. Conversely, falling into these wells makes them appear hotter. This effect isn't just a curiosity, it's a smoking gun for how gravity shapes the universe's large-scale structure. By comparing the CMB's temperature map with surveys of galaxies, scientists have verified that matter distorts space-time exactly as Einstein predicted, even across billions of light years. But the real magic lies in what the CMB hasn't shown us yet. Some theories of modified gravity, alternatives to relativity, predict subtle differences in how the CMB's patterns should look. So far, Einstein's theory wins, but future telescopes could uncover deviations that hint at quantum gravity or extra dimensions. Whether confirming relativity or challenging it, the CMB remains our most powerful tool for probing gravity's reign over the cosmos. It's as if the universe handed us a flashlight, not just to illuminate its past, but to test the very laws that hold it together. Before the cosmic microwave background was discovered, cosmology was a battlefield of competing theories. The Big Bang wasn't the only game in town. Rival ideas like the steady-state model held sway, proposing a universe with no beginning or end, where matter continuously popped into existence to fill the gaps as space expanded. But in 1964, when Arno Penzias and Robert Wilson stumbled upon that faint microwave hiss with their radio antenna in New Jersey, they didn't just solve a technical glitch, they handed scientists the smoking gun that would silence the debate once and for all. Here's why the CMB was such a knockout punch. The Big Bang theory had made a bold prediction decades earlier. If the universe began in a hot, dense state, the remnants of that primordial fireball should still linger as cooled radiation, bathing the cosmos in microwaves at just a few degrees above absolute zero. When Penzias and Wilson's persistent noise matched that prediction perfectly down to the exact temperature, it wasn't just a coincidence. It was confirmation that the universe had, in fact, exploded from an unimaginably hot and dense starting point. The steady-state model, with its elegant but incorrect vision of eternal cosmic equilibrium, simply couldn't account for this all-pervading glow. Opponents scrambled to adapt. Some suggested the radiation might come from other sources, interstellar dust perhaps, or scattered starlight, but these explanations crumbled under scrutiny. The CMB's spectrum was too perfect, matching the precise blackbody curve expected from a cooling fireball. Even more damning, the signal came from every direction with eerie uniformity, just as the Big Bang predicted. No alternative theory could explain why the entire sky should hum with microwaves unless the universe had once been a seething, ultra-dense furnace. The impact was seismic. Within a few short years, the Big Bang went from being one hypothesis among many to the cornerstone of modern cosmology. Skeptics like Fred Hoyle, who had famously coined the term Big Bang as a dismissive jab, found their objections melting away under the weight of evidence. By the 1970s, even holdouts had to concede the CMB wasn't just background noise. It was the echo of creation itself, a relic so definitive it rewrote the textbooks. What's often forgotten is how close we came to missing this revelation. Penzias and Wilson weren't cosmologists, they were radio engineers troubleshooting antenna static. Without their dogged pursuit of an annoying signal, the CMB might have languished undiscovered for years, leaving the Big Bang's critics room to maneuver. Instead, their accidental discovery became the linchpin that locked the theory into place, proving once and for all that the universe had a dramatic, explosive birth. And in doing so, it transformed cosmology from a speculative playground into a precision science, one where the faintest whispers of microwaves could rewrite our understanding of everything. The cosmic microwave background might hold the key to one of the universe's most elusive mysteries, the existence of primordial black holes. These hypothetical objects, no larger than an atom but as massive as a mountain, could have formed in the chaotic first moments after the Big Bang, when extreme densities allowed tiny fluctuations to collapse directly into black holes. If they exist, these ancient relics would have left subtle fingerprints on the CMB, warping its light in ways we're only now learning to detect. Here's how it works. As CMB photons travel across the cosmos, they pass through regions of varying gravitational pull. A primordial black hole with its intense gravity would act like a cosmic magnifying glass, bending the path of nearby light. This distortion creates telltale hot and cold spots in the CMB's temperature map, anomalies that can't be explained by ordinary matter alone. The effect is minuscule, like spotting a ripple in a pond from a single raindrop. But with sensitive enough instruments, these imprints could reveal black holes too small and ancient to see by any other means. What makes this idea so compelling is its connection to dark matter. If primordial black holes are abundant enough, they could account for some or even all of the universe's missing mass. Unlike other dark matter candidates like WMAP or actions, these black holes wouldn't require new physics to exist, just the right conditions in the early universe. The CMB offers a way to test this theory without chasing particles in underground labs or particle colliders. By scouring its patterns for the unique distortions left by these gravitational potholes, scientists could finally confirm whether dark matter has been hiding in plain sight all along. The hunt is already underway. Telescopes like the Atacama Cosmology Telescope and future missions are analyzing the CMB's fine-scale structure, searching for the statistical hallmarks of primordial black holes. Some researchers have even proposed that certain large-scale anomalies in the CMB, like the cold spot, might be scars from collisions with these ancient objects. Others suggest that if primordial black holes clustered in the early universe, their collective gravity could have subtly shifted the CMB's acoustic peaks, leaving a faint but measurable trace. Yet the implications go beyond dark matter. If primordial black holes are real, they could solve other cosmic puzzles like the origins of supermassive black holes lurking at the centers of galaxies. These behemoths, weighing billions of suns, appear too large to have formed so quickly after the Big Bang. But if they grew from primordial seeds, the timeline suddenly makes sense. The CMB could be the missing link, revealing how the universe's smallest black holes became its largest. Of course, not everyone is convinced. Critics point out that no direct evidence for primordial black holes exists yet, and alternative explanations for CMB anomalies, like cosmic strings or exotic fields, remain plausible. But that's the beauty of the CMB. It's a living archive preserving clues from every era of cosmic history. Whether primordial black holes are confirmed or ruled out, the search itself pushes the boundaries of what we know about gravity, particle physics, and the universe's wild infancy. For now, the CMB keeps its secrets close, but with every new observation, we peel back another layer, inching closer to answers that could rewrite our understanding of dark matter, black holes, and the origins of everything. And if those answers lie in distortions older than stars themselves, well, that's a discovery worth waiting for. Those delicate ripples in the cosmic microwave background, those infinitesimal hot and cold spots aren't just cosmic static. They're the architectural blueprints for everything we see in the universe today. Each fluctuation, some no larger than 1 part in 100,000, marks a region where matter was slightly denser or sparser in the infant cosmos. Over billions of years, gravity amplified these tiny differences, sculpting them into the galaxies, clusters, and vast cosmic webs that span the observable universe. It's like watching a time lapse of a forest growing from scattered seeds, except these seeds were planted in the fabric of spacetime itself, and the forest is the entire cosmos. Take the CMB's coldest patches, for example. These correspond to regions where matter was thinnest in the early universe, cosmic deserts where gravity had less to work with. Over eons, these underdense areas evolved into the sprawling voids we observe today, enormous bubbles of near-empty space stretching hundreds of millions of light-years across. Meanwhile, the slightly warmer spots, those where matter was marginally denser, became the gravitational anchors for galaxies. Gas and dark matter pooled there, drawn together by their own gravity, until they ignited into stars and coalesced into the glittering cities of light we now call galaxy clusters. The fingerprints of this process are everywhere. The CMB's fluctuations align almost perfectly with modern galaxy surveys, matching the distribution of matter so precisely it's like comparing a sketch to the finished painting. But how do we know this connection is real? The evidence comes from cross-referencing CMB maps with three-dimensional surveys of the universe's large-scale structure. Projects like the Sloan Digital Sky Survey have charted the positions of millions of galaxies, revealing a cosmic web of filaments and nodes, a pattern that mirrors the CMB's primordial fluctuations blown up to galactic proportions. Even more striking, the statistical properties of these structures, the spacing between clusters, the sizes of voids, match predictions derived from the CMB's tiny temperature variations. It's as if the universe left us a recipe where the ingredients, the CMB's anisotropies, and the final dish, today's cosmic web, are separated by 13 billion years of cooking time. What's revelatory is the scale of this transformation. The CMB's fluctuations might seem insignificant, a mere 1/100,000th of a degree, but they were the universe's only unevenness at a time when matter was distributed with near-perfect smoothness. Without those minuscule density variations, gravity would have had nothing to amplify, and the cosmos might have remained a featureless haze forever. The fact that we exist to ponder this is proof of their importance. We're the products of those ancient overdensities, forged in the slight gravitational eddies of a universe that was, against all odds, just lumpy enough to create us. And the story doesn't end there. The CMB's anisotropies also encode the role of dark matter in this cosmic drama. Because dark matter doesn't interact with light, its gravitational pull shaped the CMB's patterns in ways visible matter alone couldn't. By analyzing the spacing and amplitude of the fluctuations, scientists confirmed that dark matter must outweigh ordinary matter 5-to-1, a ratio later verified by galaxy rotation curves and gravitational lensing. Even dark energy leaves a trace. Its repulsive force altered how structures grew over time, imprinting subtle deviations in the CMB's large-scale patterns. So when we look at the CMB's mottled sky, we're not just seeing a relic of the past, we're holding a mirror to the present, one that reflects the invisible scaffolding of dark matter, the push of dark energy, and the glittering structures they've built together. Every galaxy, every cluster, every filament of the cosmic web whispers back to those primordial fluctuations, proving that the universe's grandest designs were written in microwaves long before the first star was born. The cosmic microwave background won't shine forever. Like an ember cooling in the dark, this ancient glow is slowly fading, its light stretched thinner with each passing eon as the universe expands at an accelerating rate. Right now, we detect it as faint microwaves, but in the distant future, even those whispers will vanish first into the radio spectrum, then into nothingness. This isn't just poetic metaphor, it's an inescapable cosmic truth written into the equations of general relativity and confirmed by the CMB's own redshift. Consider what's already happened since recombination. The CMB's light, once visible to the naked eye as a brilliant orange-white glow, has been stretched 1,000-fold into microwaves we need sensitive instruments to detect. But the expansion isn't stopping. As dark energy continues pushing galaxies apart, space itself will stretch the CMB's wavelengths even further. In about 100 billion years, the radiation will redshift into long radio waves, undetectable to any telescope resembling ours today. Fast forward 1 trillion years, and those photons will have elongated so much that their wavelengths could span entire galaxies, rendering them effectively invisible, their energy dispersed into the cold vacuum of an ever-expanding cosmos. What makes this process so profound is its irreversibility. Unlike stars that reignite or galaxies that collide, the CMB's fading is a one-way trip. Future civilizations, if any exist, will inhabit a universe with no natural record of its fiery birth. The night sky won't just be missing the CMB, it will offer no clue that such a phenomenon ever existed. Distant galaxies will have redshifted beyond visibility, and the universe's expansion will have erased all evidence of the Big Bang, leaving only local clusters of stars against an inky, apparently eternal void. This isn't just about losing a scientific curiosity. The CMB's disappearance will fundamentally alter how intelligent beings understand the cosmos. Imagine trying to deduce the Big Bang without seeing the redshift of galaxies or detecting the afterglow. Future astronomers might conclude the universe is static and infinite, just as pre-20th century scientists did. The very clues that led us to our current understanding will have evaporated like footprints washed away by an incoming tide. Yet there's a strange beauty in this impermanence. We live in a privileged era, cosmically speaking a brief window when the universe is young enough to still glow with its birth heat, but old enough to have forged complex structures like galaxies and planets. The CMB's fading isn't a flaw, it's a natural consequence of a dynamic, evolving cosmos. And while future observers might never know the full story of creation, we here, now, have been granted front-row seats to the greatest show in the universe, the chance to decode its origins before the evidence vanishes forever. So when we study those microwaves, we're not just doing science, we're preserving a cosmic memory that one day will exist nowhere except in the records of civilizations bold enough to have read the sky before the light went out. The term Big Bang might sound like the perfect name for the explosive birth of the universe, but it wasn't meant as a compliment. In fact, it was coined as a sarcastic jab by British astronomer Fred Hoyle, one of the most vocal opponents of the theory. During a 1949 BBC radio broadcast, Hoyle dismissed the idea of a sudden cosmic origin, arguing instead for his steady-state model, a universe with no beginning or end. These theories are based on the hypothesis that all the matter in the universe was created in one Big Bang at a particular time in the remote past, he quipped, his tone dripping with skepticism. Little did he know his offhand phrase would outlive the theory he championed. Thanks to the cosmic microwave background's undeniable evidence, Hoyle's disdain wasn't just academic sniping. At the time, the Big Bang theory was still speculative, lacking the smoking gun that would later arrive with the CMB's discovery. To Hoyle and other steady-state proponents, the idea of a singular cosmic explosion seemed messy, even unscientific. How could everything space, time, matter spring from nothing? His Big Bang remark was meant to ridicule, framing the theory as more of a cartoonish spectacle than rigorous physics. Ironically, the name stuck precisely because it captured the public's imagination even as the science behind it solidified. The cosmic microwave background turned the tables completely. When Penzias and Wilson accidentally detected the CMB in 1964, they handed Big Bang theorists the evidence they'd been missing, a relic of that primordial fireball, cooled but unmistakable. Suddenly, Hoyle's derisive label became a badge of honor, shorthand for the universe's violent, dramatic origins. The CMB didn't just validate the theory, it elevated the term Big Bang from a punchline to a cornerstone of cosmology. Hoyle, to his credit, never fully conceded. Even as the CMB's blackbody spectrum and uniformity piled up evidence against his steady-state model, he tweaked his ideas, proposing alternative explanations for the radiation. But with each new observation, the CMB's fluctuations, its perfect alignment with Big Bang predictions, his resistance grew lonelier. By the time he passed away in 2001, the name he'd coined in mockery was etched into textbooks worldwide, a testament to how thoroughly the universe had outmaneuvered him. There's a delicious irony in this story. The man who fought hardest against the Big Bang ended up naming it, while the discovery he dismissed as impossible became its most definitive proof. Today, the term is so iconic that few remember its origins as a scientific insult. And the CMB, it's the ultimate punchline, a cosmic mic drop that silenced the critics and turned a sarcastic quip into the most famous phrase in cosmology. So the next time you hear Big Bang, remember, sometimes the universe has a sense of humor too. What if the cosmic microwave background isn't just a relic of our universe but a message from others? Among the CMB's subtle anomalies lies a breathtaking possibility. Some of its quirks, like the infamous cold spot or unexpected temperature asymmetries, might be cosmic bruises left by collisions with other universes. This isn't science fiction. It's a legitimate thread of multiverse theory, where our cosmos is just one bubble in an infinite froth of spacetime, each with its own laws of physics. And if these bubbles bumped into one another in the early universe, the shockwaves could have left imprints in the CMB, like fingerprints on a window between worlds. The math behind this idea is as elegant as it is mind-bending. Inflation theory, the same framework that explains the universe's smoothness, predicts that rapid expansion could have spawned countless bubble universes beyond our own. Think of boiling water. Steam bubbles form, grow, and sometimes collide. In the cosmic version, these bubbles are entire universes, each nucleating in a higher dimensional bulk space. If one grazed ours during inflation, the energy of that collision could have warped our universe's fabric, leaving behind telltale distortions in the CMB's temperature and polarization patterns. The cold spot is a prime candidate for such a scar. Stretching nearly 2 billion light-years across, this region is colder than standard cosmology can explain. Some researchers suggest it could mark the point where another universe's bubble brushed against ours, injecting energy that altered how matter clustered in that area. It's like finding a dent in a car door, evidence of an impact, even if the other vehicle is long gone. Other anomalies, like the CMB's lopsided hemisphere temperatures or unusual large-scale patterns, might also hint at these collisions. But proving it isn't simple. Alternative explanations exist: cosmic voids, exotic dark matter interactions, or even statistical flukes. What makes the multiverse hypothesis compelling is its predictive power. Theorists have calculated how bubble collisions would distort the CMB, creating circular temperature patterns or specific polarization swirls, and future telescopes could hunt for these signatures. Projects like the Simons Observatory or next-generation space missions aim to scan the CMB with unprecedented precision, turning these speculations into testable science. Critics argue the multiverse is untestable by definition. If other universes are forever beyond our reach, how can we ever confirm them? The CMB offers a loophole. If collisions happened within our cosmic horizon, their remnants might still be visible, frozen in microwaves. It's a long shot, but so was the Big Bang theory before Penzias and Wilson found its afterglow. Whether these anomalies reveal other universes or just deeper layers of our own, the pursuit itself reshapes how we see reality. The CMB isn't just a snapshot of our origins, it might be a mosaic pieced together from fragments of countless other cosmoi. And if that's true, the universe's oldest light isn't just whispering secrets about our past. It's carrying echoes from neighbors we'll never see, but whose existence could rewrite everything we know about existence itself. The cosmic microwave background isn't just a window to the past, it's a treasure map for the future. And scientists are racing to decipher its remaining secrets with missions so advanced they'd sound like science fiction a generation ago. Leading this charge is CMB-S4, a next-generation observatory network that'll scan the microwave sky with 10 times the sensitivity of current instruments. Imagine trying to hear a whisper in a hurricane and then suddenly upgrading to a microphone that can isolate every individual raindrop sound. That's the leap this project represents, and its targets read like a cosmologist's wish list: primordial gravitational waves, signs of dark matter particles, even echoes from universes beyond our own. What makes CMB-S4 so revolutionary isn't just its scale, it's the sheer audacity of its goals. Deploying telescopes across Chile's Atacama Desert and Antarctica's South Pole, it'll map the CMB's polarization in microscopic detail, hunting for twisted swirls called B modes. These delicate patterns could be the smoking gun for cosmic inflation, the theory that the universe expanded faster than light in its first trillionth of a second. But here's the catch: these signals are fantastically weak, drowned out by galactic dust and the CMB's own glare. CMB-S4's 500,000 detectors, chilled to near absolute zero, will filter this noise like never before, offering our clearest shot at proving inflation happened, or discovering it didn't, which would be even more shocking. Yet gravitational waves are just the start. The same data could reveal actions, hypothetical particles that might make up dark matter by their subtle interactions with CMB photons. It might spot neutrinos from the universe's first second, fossils from when matter and antimatter nearly annihilated each other. Some theorists even think CMB-S4 could detect cosmic strings, defects in spacetime left over from the Big Bang, whose gravitational tugs would warp the CMB in telltale ways. Each possibility hinges on spotting deviations so minute they'd be like measuring a human hair's width from orbit. But that's precisely why this mission is being called the Hubble Telescope of Microwave Astronomy. And the ambition doesn't stop at hardware. By cross-referencing CMB-S4's findings with gravitational wave observatories like LIGO and dark matter experiments deep underground, researchers hope to weave a unified picture of cosmic history. For example, if primordial B modes align with certain particle detector signals, it could prove that dark matter influenced the early universe's expansion. Or if CMB anomalies match up with oddities in galaxy distributions, we might finally understand why the universe's expansion rate is accelerating. This isn't just observation, it's cosmic detective work on a scale we've never attempted. The stakes couldn't be higher. If CMB-S4 detects nothing, it'll force us to scrap cherished theories about inflation and dark matter. But if it succeeds, we'll have tapped into the universe's oldest light not just as a relic, but as a live feed from the edge of physics itself. Either way, the answers, or the lack thereof, will redefine our place in the cosmos. Because while the CMB has already rewritten textbooks, its greatest revelations might still be hidden in those faint microwaves, waiting for the right tools, the right minds, and the right moment to share them. The cosmic microwave background isn't just a scientific curiosity, it's humanity's closest thing to a time machine, offering us a front-row seat to the universe's very first moments of clarity. When we study this ancient light, we're not just analyzing data, we're witnessing the exact instant the cosmos transitioned from a seething, opaque plasma to a transparent universe where light could finally travel unimpeded. That pivotal moment, known as recombination, happened when the universe was a mere 380,000 years old, a cosmic blink after the Big Bang. Before then, space was so dense with charged particles that photons couldn't travel more than a fraction of an inch without being absorbed and re-emitted, trapping light in a chaotic dance. But as the universe expanded and cooled, electrons and protons combined into neutral hydrogen atoms, and like a fog lifting, the skies cleared. The light that broke free at that instant is what we now detect as the CMB, carrying with it an unfiltered snapshot of the universe's infancy. What's staggering is how immediate this connection feels. The photons hitting our telescopes today have been traveling for over 13 billion years, unwavering messengers from a time before galaxies, before stars, even before atoms as we know them existed. In a very real sense, when we map the CMB, we're not just looking at a picture of the early universe, we're interacting with it. Every subtle fluctuation in temperature, every polarization pattern, is a direct signal from that primordial dawn, unaltered by the chaos of cosmic evolution that followed. It's as if the universe left us a voicemail from its birth, and we're only now learning how to play it back. This isn't just a theoretical abstraction. The CMB's light bridges past and present in ways that feel almost poetic. Consider that the static on an old analog TV, that snowy hiss you might remember from childhood, contains traces of this ancient glow. Every time someone tuned into a dead channel, they were inadvertently bathing in photons older than the Earth itself. Even now, the CMB surrounds us, invisible yet omnipresent, a whisper from the dawn of time passing unnoticed through our bodies, our homes, our planet. We're literally swimming in the afterglow of creation, a thought that transforms the mundane into the extraordinary. But the CMB's true gift isn't just its age, it's its clarity. Unlike starlight, which gets scattered and distorted as it travels through galaxies and dust clouds, the CMB comes to us almost pristine, its signal barely touched by the universe's later tumult. This purity makes it the ultimate benchmark for cosmology, a yardstick against which we measure everything from the universe's expansion rate to the nature of dark matter. Without it, we'd be like archaeologists trying to reconstruct a civilization from fragments buried under centuries of upheaval. The CMB, by contrast, is like discovering an untouched tomb, its contents perfectly preserved, offering an unobstructed view into a vanished era. Perhaps most profound is how this ancient light collapses time, connecting us directly to events that unfolded billions of years ago. When astronomers study the CMB, they're not just peering into the past, they're participating in a chain of causality that stretches back to the universe's first breath. Those photons didn't just happen to reach us, they were forged in the fires of the Big Bang, then spent eons racing through an expanding cosmos, only to land precisely here, now in our detectors, as if the universe itself arranged for us to receive them. In that way, the CMB is more than a relic, it's a bridge, a thread tying our present moment to the very origins of everything. And as we continue to decode its secrets, we're not just learning about the universe, we're rediscovering our place within it, a story written in microwaves, waiting 14 billion years to be told. From the moment we first detected its faint glow, the cosmic microwave background has rewritten the story of our universe. It's not just radiation, it's the ultimate witness, a time capsule preserving the cosmos's fiery infancy with astonishing clarity. Every fluctuation in its temperature, every twist in its polarized light, has peeled back layers of cosmic history, revealing how galaxies formed, how space expanded, and even hinting at invisible forces like dark matter and dark energy that still mystify us today. Without this ancient light, cosmology would be like navigating without a map. The CMB didn't just fill in the blanks, it gave us the entire blueprint. Yet for all we've learned, the CMB whispers of mysteries still unsolved. Why is the universe's expansion accelerating? What exactly is dark energy, that enigmatic force pushing galaxies apart? And could those strange anomalies in the CMB, the cold spot, the uneven hemispheres, be clues to physics beyond our current understanding, or even evidence of other universes? The more we study this primordial glow, the more questions it sparks, reminding us that every answer unlocks new riddles. But here's what's truly humbling. The CMB connects us directly to the universe's origins. Those photons traveled for billions of years through the birth and death of stars, the rise of galaxies, the formation of planets, just to reach us now, a fleeting moment in cosmic time when intelligent life emerged to decode their message. It's a reminder that we're not just observers of the universe, we're part of its unfolding story, born from those same quantum fluctuations imprinted in the ancient light. So the next time you look up at the night sky, remember, you're not just seeing stars, you're seeing the aftermath of that first burst of light, the echoes of creation itself. And with groundbreaking telescopes like CMB S4 on the horizon, who knows what secrets we'll uncover next? The universe's oldest light still has stories to tell, and we're only just learning how to listen. If this journey through cosmic history sparked your curiosity, don't stop here. Hit like, subscribe, and dive into the comments what fascinates you most about the CMB. Is it the lingering mysteries, the mind-bending scale, or the sheer luck that we exist in a sliver of time where we can decode the universe's origins? Let's keep the conversation going. After all, the story of the cosmos is your story too.